Students, today we are going to start the final chapter on electricity and magnetism and the final chapter for the course. This is a very important chapter. Electromagnetic induction is one of the most important principles. It's the source of how we make electricity, which we'll talk about, and perhaps the most important of all of the equations that we use. Without further ado, let me just start off by saying that some of the things that we'll talk about in this lecture will be the principle of electromagnetic induction, its description by as Faraday's law, who was the discoverer of this property, how we use this property or law to make electrical generators and to generate alternate current that is being delivered to houses and factories and all manner of electrical requirements. We'll talk a little bit about how it's used in power production and also things like power transmission and these other two items, self-induction and field induction. So without much ado, let's go ahead and get started. Faraday's law of magnetic induction was discovered by an experiment similar to this by shaking a permanent magnet inside a coil and finding that if you shake this magnet up and down inside the coil, then there is a current that is produced and there is a voltage between the ends of the wire. Obviously those two go hand in hand. We need to have potential difference across 2 points in order to provide the electrical pressure to generate current. So it induces voltage in a wire by changing the magnetic field strength in the coil. When the magnet is completely pulled out, the field strength is 0. When it's completely inserted, it's maximum. And that change in the magnetic field in the coil is what generates the voltage. And another way to state a Faraday's law is that the voltage that is induced across the ends of the wire, the potential difference between one end and the other, is equal to the number of loops, how many turns we have in the coil, times the area, the cross-sectional area of the circle within each loop, times the rate of change of the magnetic field. It's a dynamic process. It only occurs when the field is changing with time. So what exactly is the change in field times area with respect to time? Notice I put the area back inside the derivative or differential sign again. It's actually BA is the field strength, which are indicated by the dashed lines, times the area of the loop viewed from the direction of the magnetic field. So what that means is that if I look at the first loop of current, a loop of wire on the left, there's the magnetic field, and the area that is exposed to the magnetic field is maximum because it is going perpendicularly through the surface of the plane defined by the loop of wire. If, on the other hand, we allow that coil to rotate by 90 degrees, then there are no field lines crossing through perpendicular to the area of the loop. And it is that effect which we look for and which defines what we mean by the field times the area. So in this case, the field times the area is 0 because even though there is a magnetic field, there is no field that is crossing perpendicularly to the area of the loop. Whereas in this case, the field times the area is maximum. It's the external magnetic field that's applied times the area of the loop because all of the field lines are perpendicular to the plane of the loop. So here we have maximum B, field times area. Here we have minimum field times area, or 0. Here it's maximum again, it's 0, it's maximum, etc. So this has the effect of inducing a voltage where the strength of the voltage is proportional to how rapidly the area as seen by the magnetic field, if you imagine the magnetic field being viewed from the left, that how rapidly the area of the loop is changing with time as seen from the left side of the screen. This is how we generate a time-changing magnetic or flux, we should say. This product B times A is also referred to as magnetic flux, so we can refer to the product and the effect as the time rate of change, how quickly the flux through the loop is changing. Another important feature of all this is that you have to do mechanical work to rotate the wire to make current flow in the wire. This is not simply due to the friction in the turning crank that you may use to cause or push this wire through a rotation cycle, but it was also going to be due to the magnetic resistance of the loop itself to fight the induced EMF or to resist the change that is occurring. So the idea of that you have to do mechanical work for your input is required to get electrical energy as your output. And consequently, this is also why we have to pay for electricity. Electricity does not come free. It isn't just the cost of the wires, it's actually making the voltage at the power plant. The voltage or current is sinusoidal, and hence we call this an alternating current. Now there are several ways we can change or increase the induced voltage from Faraday's law. We can increase the number of loops of wire in a coil. That is one way of doing it. If we increase the number of loops, that will increase the voltage. We can increase the speed of the magnet entering and leaving the coil. This refers to this, not the last slide, but the slide before, where we treat the magnet as a plunger going in and out of the coil. And if I increase the speed of raising and lowering that magnet, oscillating it in and out of the coil, that will also induce more voltage because the rate of change of the magnetic field is increasing. So as a result, we get the observation that slow motion produces hardly any voltage. Rapid motion will produce more. And as the magnet goes up and down, or the loop of wire is rotated, which is what was the last example, then the voltage in the wire swings from positive to negative at the frequency of the magnet's motion. So this is how we generate voltage, but it's going to be generated, as we saw on the last slide, as a sinusoidal variation in voltage with time as a result of flipping this loop around and over again, or as a result of shaking the magnet up in and out of the coil at a given frequency. So this is how we do it. Now, when a magnet is plunged into a coil with twice as many loops as another set of coils, there's twice as much voltage induced. And that's basically what we said in the last slide. But here you can see that in comparing these three different graphs, the one with the most coils on it is going to give the largest amount of voltage across the wire. Now, if the magnet is plunged into a coil with 3 times as many loops as we have on the left compared to the one on the right, then there'll be 3 times as much voltage. Whereas the one in the middle has only twice as many coil turns of coil as the one on the left. So Faraday's law of induction states that the induced voltage in a coil is proportional to the number of loops, which we call N, multiplied by the rate at which the magnetic field times the area, where we mean the area, the circular area of the loop, changes within those loops. We want to then, we can write this mathematically by saying that the induced voltage is equal to the number of coils, or the number of turns in the coil, times the rate of change of the flux, which is magnetic field times the area. And this is a further statement of Faraday's law. Now, the amount of current produced by magnetic induction depends on the resistance of the coil. Obviously, we will get the voltage that is defined by this equation, but if the material in the coil has a lot of resistance, or if there are a lot of turns in the coil, then that will reduce the current that is generated. So it's dependent on the resistance, the circuit that it's connected to, because the rest of the circuit will have a light bulb or something with another high resistor in it. That affects the current as well. And it is also obviously dependent on the amount of induced voltage, which gets back to the equation written above. So it is more difficult to push the magnet into a coil with many loops because the magnetic field of each current loop resists the motion of the magnet. So this means simply that this woman here is looking somewhat astonished, because if she were simply to plunge or shake the magnet up and down vertically without the coil here, it would be a relatively simple task and she would not feel any extra work needed to be done. But as soon as she plunges it into a coil, then there is a magnetic field that is generated in the coil because of the current. So the magnet plunging in here causes current to flow, and that current, it creates a magnetic field which reacts on the magnet, resisting that change. And by resisting that change, she's experiencing this as having to do more work or more force. So therefore, you can see directly from this that it takes mechanical work in order to make electricity. Now, voltage induced in a wire requires changing magnetic field through the loop by either moving the loop near a magnet, moving a magnet near a loop, rotating a loop in a magnetic field, as what we have seen. And all of these yield a generation of potential, electrical potential, which we call voltage. And that is a statement also of Faraday's law. And we've seen that in a couple of examples already. Now, generators and alternators, or we'll talk about generators here first, basically are devices that convert mechanical energy to electrical energy. And they can do it by, you can buy a generator at a store that uses gasoline power. People use generators if they want to go to a cabin out in the woods where there's no electricity. Just bring the generator and a tank of gasoline to keep it operating. And it provides the mechanical motion to turn this loop of wire in a magnetic field. When that occurs, and as a result of the mechanical energy of turning this loop of wire, we get a potential difference across here, which, connected to a device, will then illuminate a light bulb as a result of the current flow. And that current is made possible by the fact that these ends of the wires of the loop are getting a potential voltage as a result of the loop that is turning in the magnetic field. So this is one way in which we can make electricity. And as I said before, well, you can buy little toy gadgets in the store where if you need to get a flashlight that doesn't have any batteries, you can buy the ones that where you simply turn a crank and the light will generate, and therefore you never need a battery, you only need your arm available to turn the crank that will cause this loop of wire to rotate in the magnetic field. We've already said, the only thing I would add to this slide that we've seen before is that when we generate electrical power for at the power station or in a generator, we typically use an agreed upon standard of the frequency of the voltage. So the number of times the voltage goes up and down per second is given, determines the frequency, and that turns out to be 60 cycles per second. So if I'm at a fixed point along the line, I can observe 60 oscillations of the voltage per second. And this is equal to the frequency of the loop rotating in the magnetic field. And this is the way electricity is generated throughout our power plants. Power production is a very important result of this Faraday's law of magnetic induction. It is the source of how we get all the electricity that we need in the world. And the demand for electricity in the United States is very strong. Approximately, we use on average 1 trillion watts of power in the US to supply 300 million people. So whatever that ratio is tells you how many watts is needed per person. Roughly speaking, we typically use about 10 kilowatts per person in the United States. And that's every day, every minute, every hour of the day. We are very large consumers, and as a result, we need a way to generate all this electricity. Now, all of this comes down to finding a way to spin a coil or a loop of currents or group of currents in a magnetic field, such as you see here. So in other words, we have to find a way to make these coils spin in a magnetic field. And as I mentioned, there's the opposition force that once you try to turn this, which you can do, it requires a lot of work to turn this, because the current that is generated here is opposing the change in such a way that it resists the motion that you're trying to create. But in any case, the difference in power generation is all about how we make the steam. So steam requires, imagine here that what is actually happening for our electricity generation is that we need to generate a powerful stream of gas, and normally that gas is water vapor, but it doesn't have to be, but a powerful stream of high pressure gas that impinges upon the blades of a turbine that acts like a fan and causes the fan to spin. And as the fan spins, it is connected but through a shaft to the coils of the wire, which is how the voltage gets generated on the output. Making this steam is of course crucial, and of course the point at which we are looking at in order to make electricity. So how can we make steam a high pressure nozzle or stream of water vapor to cause this thing to turn? Well, the traditional way is that we burn coal. So imagine that we have a power plant with a great big oven furnace, and you keep dumping coal in there. So that as the coal burns, it heats up the water turns to steam. There's a pressure vessel, sort of like those pressure vessels on your stove, that convert that to a high pressure stream of water vapor coming off the top, and that is directed at the turbine or the fan. Obviously this has a downside. Burning coal is a way of doing it, but we pollute the air at the same time. It produces a lot of hydrocarbon emissions that then mix in the atmosphere and cause global warming to occur. We talked about that in the thermodynamics section of the course, and that global warming is producing some very negative detrimental effects, such as rising seawater levels and increased diseases from mosquito-borne and other insects that will proliferate faster as we generate a warmer climate. All these things lead to negative effects. So there are other ways in which we can do that. Nuclear reactors are one of them. They have had their downsides as well. Those of you that watch TV series may have seen the show Chernobyl, which was a very serious reactor failure in the 1980s that caused a large number of deaths. Now, at the same time, we have many more deaths occurring from miners mining coal and getting lung diseases. So nothing is free of risk. But we need something to generate steam. So nuclear reactors can do it. You can make the material around these nuclear reactions get very, very warm as a result. Obviously not in the sense of an explosion, but in the sense of a controlled heating up of the environment. And that also will generate the stream of air that we want. Another one that's being actively used is wind power. So we could actually just use, instead of steam, we could just use windmills. And windmills are gaining importance throughout the industry, our world as well. But we're looking for alternatives, and the most useful alternative will be solar power, and we've talked a little bit about that before. But this is how we generate power in electrical power plant. By the way, in the area in which we live, which is in the Chicago area, 70% of the power is nuclear, comes from nuclear reactors, and only 30% is produced by burning coal. So we live in a fairly clean environment, provided we don't have any unsafe nuclear accidents, so to speak. Okay, so enough about that. The turbine is connected to a loop of wires, forced to spin the magnetic field, and that, of course, is how we generate the electricity.